Hello everyone. So we've gone over two different representations of 3D rotations now. So the first one was this roll, pitch, yaw, where we had these interconnected gimbals, and we saw that we could give three angles and reach any rotation, and I gave you an equation to solve for what those angles should be. The other representation is of the rotation matrix that you get. So you could forget about the angles and just look at, okay, what do you get when you actually take the product of the three matrices that do those rotations? And you're going to get a matrix like this, where each column can be thought of as a vector representing one of the axes. So the x-axis goes to this red vector here, the y-axis goes to the green one, the z-axis goes to the blue one. And I'm depicting that coordinate system here. And what you notice about it is these vectors are mutually perpendicular. They're each length 1, and they maintain a right-handed coordinate system. So we would say that this matrix has a determinant of +1, in addition to these vectors being mutually perpendicular. Okay, so we have the three angles that we can specify. We have the rotation matrix. Now there's another representation I want to tell you about now, which will be very useful when we think about interpolating between two different rotations. So let me just set up a matrix here. This one seems fine. And I'm going to copy this matrix over into Python. So let me go ahead and make a matrix like this. So I'll say, okay, R is equal to, so I'm going to use NumPy here. So I will create a two-dimensional array with those entries that I just came up with there. And, okay, so I'll just format that real quick. All right, so I got my matrix here. And so it turns out there's a very special vector that's associated to every valid rotation matrix. So let me have a look at that. I can compute it actually with something called the eigenvectors of this matrix. So eigenvectors, I'll compute them with this library here. These are vectors that stay in the same direction when we multiply them by this matrix. And in NumPy here, each one of those vectors is going to get stacked up in a column of this matrix V that it's sending me back. So let me focus on this first vector here. So let me pull that out. So the first column there. I look at this vector. It's got some weird stuff here, +0j. I'll talk about that in the next video. These are complex numbers here. This is an imaginary number. But it's 0, so I don't actually have to worry about it for this vector. So I'm just going to say, take what's called the real component. And this is really the vector that I'm talking about here. Okay, so I told you that this is a vector that when I multiply it by the matrix R, it's supposed to stay in the same direction. So let me just look at what I get. And so aside from some rounding errors that I probably mostly incurred actually over here, aside from some rounding errors, not only are these in the same direction, they actually are the same vector. So it's interesting. I found a vector that stays fixed when I multiply it by this matrix. So this is going to happen for any valid rotation matrix in 3D that I have. So there's something called Euler's theorem, which says that for a given 3D rotation matrix, R, there exists a vector A, so that RA is A. All right? So in other words, there is a vector, actually exactly one vector, that stays fixed when we apply this rotation matrix. Oops, sorry, my head was in the way. When we apply the rotation matrix. Okay, so that's called Euler's rotation theorem. Actually, Euler's got a lot of theorems, so I should say Euler's rotation theorem. Quite a prolific mathematician. Okay, cool. I mean, but that's kind of interesting, because that would never happen in 2D. So if I go back to my little widget here showing the 2D stuff, I mean, every single vector, unless it's the trivial matrix, the identity matrix, every single vector I could possibly draw will change. It will rotate. But something different is happening in 3D. So somehow we're saying there's a vector I can choose that under this 3D rotation stays fixed. So it turns out this vector can be thought of as the axis of rotation. So let me show you what I mean. I made another little app here that shows the result of applying a 3D rotation to this orange vector here around this gray axis. Okay, so my head, this is my head, starts off at the tip of the orange vector. And what I'm saying is, okay, every rotation matrix can actually be represented by an axis and an angle that rotates in a circle around that axis. So if I look at this from a different point of view, I can see that this is actually just a glorified circle that this thing is rotating counterclockwise around. So it starts off here and then goes around that circle. But if I were to make that vector be the axis itself, or on the axis, so if I made this, so the axis of rotation here is in the direction 1, 1, 1, been normalized here. So if I move this to 1, 1, 1, notice it doesn't go anywhere because when I rotate it, the circle is of radius 0, right? So that's really what Euler's rotation theorem is saying. It's like, okay, there is one vector, or one class of vectors. All the vectors that are along the axis of rotation stay fixed because there's just no, the circle is of 0 radius. Just to nail this point home a little further, let's say I move this out a little bit. Let me move it to 3 through 3. Same thing, but let's make the z component be maybe 3.5. So let me move it slightly off axis. And now what you see is a very small radius circle, right? So this rotation, any rotation by an angle around this axis, if I choose a vector that's slightly off the axis, I'll actually get a non-trivial result here. But if I'm on the axis, I stay fixed. That's the idea. So what you could do is send a vector through this matrix that's not on the axis, some other vector. Look at where it ends up, and that would tell you the angle. Okay, so Euler's rotation theorem boils down to saying, hey, any rotation that you choose can be represented by an axis and an angle. So actually, let me try to match this one that I made here. So the axis here is this. So let me just copy this in real quick. I'll put this in the program. We'll see where this axis ended up being. And okay, so there's the axis. It's pointed a little bit down. It's in this XZ quadrant here. Whoops, okay, my program, I'm moving around here and the focus was on there. Okay, so there's that axis. Now I need to solve for the angle of rotation. And so like I said, I could send through some other vector. So maybe I'll just send through the vector, maybe just 1, 0, 0. And let's see where that ends up. So I'll say, okay, that was maybe, I'll call it u, and then maybe the v that's going to be r dot u. And then we can look at, we can go back to our classic dot product formula and print out the arc cosine, the inverse cosine of the dot product of these two. All right, we might as well multiply this by 180 over pi to convert to degrees. So what I'm finding is this matrix that I set up here to perform this rotation can be realized by rotating a vector around this axis by an angle of about 33 degrees. So that's another way to accomplish the rotation that I depicted here. But I want to study the axis angle representation in its own right. So regardless of, if somebody didn't give me a rotation matrix or these roll pitch yaw angles, let me just see if I can understand this rotation in its own right. So give it an axis rotating by a particular angle around it. Okay, so to do this, I want to first notice that regardless of the axis and the angle that I choose, there's always still a plane of rotation. So if I look at this from a particular point of view, it actually just looks like a rotation that's happening in the plane. So it's just a counterclockwise rotation in the plane. So if I can somehow figure out what that plane is and characterize it, then I might be able to just kind of go back to a 2D rotation, what I know about that. Okay. So to do this, let me break this down. I'm actually going to first look at it from another point of view, because I'm going to construct what's basically the x-axis of rotation, this orange line segment here. In order to do that, I need to look at it from this point of view and realize that there's a right triangle that's being created. And so let me try to recreate that in Inkscape real quick. So we've got the axis of rotation, and then we have the vector that I'm rotating. Okay, so I've drawn my axis here, and the vector I'm rotating around here. And actually, you notice I've drawn my axis a little shorter here because I want to make sure that the magnitude of the axis is always 1. You'll notice that if you go back to my program. I've always made sure that the sum of the squares of the components is 1. But actually, what I'm depicting in this program here is the projection of v onto the axis. So if I look at that, I'll call this v proj a. So let me just depict the line that this axis is part of. I'll make a little dotted line there. And then if I drop a perpendicular from this to the axis, the line containing the axis, then that gives me the projection of this vector v onto the axis a. And that's really what I'm drawing in my picture here. So let me call this v proj a. Okay, so that takes me that vector takes me to the center of rotation there, that v proj a. And I mean, I can get that simply by doing, if this is actually length 1, I can get that by doing just a dot product of a and v. And then multiplying that by a. Okay, so that's just our standard dot product rule. And now I have this other vector, which is what's left over after the projection. I'm going to call that vector c, and in this picture here, this is c. That is actually one of the axes of rotation. Really, it's the x-axis of rotation. So I'm going to color it the same way I did there. That this is an orange vector. And this is, again, what's left over when I project v onto a. So this would be v minus v proj a. I'm going to call it c, though. I'm going to give it this special name. I'm going to call it c. All right? So that's one of the axes of rotation. But if we go back to this and we look at the plane of rotation again, there's another axis that's perpendicular to that, right? So we have basically our effective x-axis, and then we also have our effective y-axis. And that's this purple vector here. So if I go back, I can look at that circle like this. I'm going to redraw c from this top-down point of view, looking at the plane of rotation. And what I'm looking for is this other axis s, so that what I can do is perform a rotation around the center here, which is at the tip of v proj a. So that's the center of the circle. And I'm going to perform a rotation between the axes c and what I'm calling s here. And to write that rotation mathematically, I would start at the center. So I would say, okay, my rotated v is going to be equal to v proj a. So that's the center, start at the center, plus the vector c times cosine of theta. Let me copy my little theta here. Plus s times sine of theta. All right, so if I knew what s was, this is the equation. And maybe I will actually add the hats over the vectors here just to make it clear where the scalar multiplication is, because the cosine theta and sine theta are scalars. I multiply my vector c and my vector s by them. All right, so this is the formula that I'll get for doing that rotation. And this is actually a version of what's called Rodrigues' rotation formula. I just need to fill in a little more detail. So how do I get that S? All right. So if I go back and look up at the picture again, I notice that axis S is perpendicular to both C, the x-axis of rotation, and the actual axis of rotation of the whole 3D matrix. So it's perpendicular to this gray vector and this orange vector. It's perpendicular to both of these vectors. So how do I construct a vector that's perpendicular to two vectors? So it'd be kind of going out like that if I were to draw it. Well, I got to take the cross product, right? That is going to give me a vector that's perpendicular to the two. I just have to get the order right so this points in the right direction, because the cross product is not commutative. So if I look, what you'll see is, okay, it's actually going to be V proj A cross C. Because if I put my fingers in the direction of V proj A and then I curl my fingers towards C, I will get a vector that points in that direction. So I can say then is that vector S is equal to V proj A cross C. All right? So I could finish this whole equation here by plugging that in, right? So what I would like to do now is implement this in code and see if we can get it to work. So what I have here is a version of the program that I showed you a moment ago, but I haven't filled in the code to actually perform the rotation. So you can see this going around, but the vector is actually not moving with it. Once I have this implemented properly, we'll get back to where we were. So I made a little method here that takes all the information I need to rotate a vector v around a particular axis by a particular angle. And in the animation, I'm just sweeping that angle forward. Okay. So I need to compute the three vectors that are going to help me here in Rodrigues' rotation formula. So let me first compute the projection of v onto the axis A. And I made a little helper method here, but it's exactly what I said. And in fact, it doesn't even require the thing to be normalized. But anyway, so I'll say, okay, v proj A is equal to that method proj v onto the axis. Okay, now I need to compute C. So that vector C, basically the x-axis rotation, is just what's left over after the projection. So I'll say let C be vec3.subtract, vec3.create. So I want to do v minus v proj A. Okay, so now I got my axis C. And then finally, I need to construct my axis S, which, if I'm very careful about this, that should be the cross product of v proj A on the left with C. So I'll say S equals v proj A comes first, and then C. Okay, great. So those are all the vectors that I need to deal with, and now I just need to compute the cosine and the sine. So for this, I know that I need to add v proj A plus C times cosine of theta, so I'll use this helper method here. So I'll say let v rot is equal to vec3.scale and add. That's a nice method I can use. It's going to return into a new vector here, and I want to start with v proj A, and I want to add to that C times the cosine of theta. And then after that, I want to say add to that, scale and add what we have so far plus S times sine of theta. So that's why I chose the letter C and S, because C goes with the cosine, S goes with the sine. This is the way that we can rotate around a general plane of rotation. As long as we construct these two axes, we can do it. Okay, so I'll go back to the code here, and I'll return this, and I'll see what I get. It looks like there's an error. So, okay, it says theta is not defined. I meant to call this, I should have called this theta. And let's see. Okay, now it's running. But this is not right. Looks like he's on a bungee cord or something. Okay, or some kind of boomerang. So let's go back and actually let's look at the math. One thing that I wasn't careful enough about was, yes, I constructed this vector s in the right direction, but in order for this to be a rotation around the circle, I need to make sure that the length of s is exactly the same as the length of c. Otherwise, it'll be a rotation around an ellipse. So let's see, what is the length of s? I didn't actually check that. So the length, if I go back to my cross product rules, the length of s is going to be the length of the first vector times the length of the second vector. Oh, now I think I see where the problem is. It's the length of the first vector times the length of the second vector times the sine of the angle between them. Okay, now the sine of the angle between them is 1 because v proj a is perpendicular to c, right? They're perpendicular. In fact, let me just draw that here just so we have it. Okay, so this is perpendicular, so that's fine. I can then get rid of the sine because a sine of 90 degrees is 1. But the problem here is v proj a is not necessarily length 1. I had the right direction here, but I should have done a cross c. Because a is of length 1. Remember, I went through a pain a second ago just to make sure that was true. So if I do that, then I get that the magnitude of s is the magnitude of a times c. Well, the magnitude of a is 1, so therefore the magnitude of s is equal to the magnitude of c. Okay, so instead of doing the cross product of v proj a with c, let me do the cross product of a with c. And hopefully that'll fix it. Let's see. So if I go back, okay, there's an error. Oh, a is not defined. Of course, I called it axis here. Okay. Do we get it? Yes, we did. Okay, that's it. Nice. Okay, cool. So you see, it's actually not so bad. You just have to break it down into these three pieces. Go back. You get the center. You get the x-axis rotation, which I'm calling c. And you get the y-axis rotation, which I'm calling s. And I've done this before, and I still made a mistake. So, but yeah, break it down, be careful, and you'll get it. So I'll provide this code. Okay, there's one more thing I want to say about this. So we started the discussion talking about how to convert from a matrix representation of a rotation to an axis angle representation. And actually, I did make a little mistake there, which would have been a little hard to explain before you saw the whole thing. But I actually want the angle between the perpendicular projection of V and the perpendicular projection of the rotated angle. So let me just fix that real quick. So let me make this, so U is equal to the perpendicular projection on the axis. So that would be U minus A times the sum of U times A, so A times the dot product. And then V would be V minus the axis times the sum of V times. Okay, so this is just the per projection of U, and this is the per projection of V. So I actually want the angle between those two vectors. That's going to be the angle of rotation of this matrix. Let me just normalize these real quick. So I'm going to make sure that their length is 1, so I can apply this dot product formula. And I'll do that to V as well. So I'm going to change V to this. And now this should be the actual angle of rotation. Okay. So I got my axis of rotation here, and this is now my correct angle of rotation. So I want to now try to go the other way. I'm going to say, okay, if this is the axis and the angle that you gave me, show me how to come up with a rotation matrix, and I'm going to check to make sure it's actually this matrix in the end. Okay. So to get to this, you can actually write this whole thing that I derived here in a different format. I'm not going to derive this right now, but it's just some vector rules. But you can rewrite the Rodrigues rotation formula like this. And if I do that, there's actually a little trick I can use, which is the cross product of some fixed vector A, so in this case the axis, with a vector x can actually be written as a linear, it's actually a linear operation. in X. So what that means is that I can write it as a matrix multiplication. And so if I let the vector A be AX, AY, AZ, if I let it be those three components, then the matrix of X by this matrix is the cross product with A. So this is what's called a skew symmetric matrix. Every element that I reflect across the diagonal here gets the negative of its element. And so that this multiplying by this matrix actually does the cross product with A. You can check this. You can go back to week 1 and look at the cross product formula that I gave you. But this, the reason that I'm doing this is because now I can actually write, I'm trying to get a matrix, right? So if I can write part of this, the cross product part of it, as a matrix multiplication, that gets me a lot closer. So let me try to work this equation here and see if I can get any closer. So every time I see the cross product of A with something, I'm just going to write the matrix multiplication A. So here was A cross V. I'm just going to write A, matrix multiplication AV. And then I had A cross that. I'm just going to write matrix multiplication of A times that. Over here I had A cross V, so I'm just going to write A times V. And I'm almost there. What I need to do is factor V out because I'm trying to come up with a single matrix that I can multiply by V and get this. And so another thing another trick here is that, well, V by itself at the beginning of this equation, it's just the identity matrix times V. That doesn't change V, right? It's just, this is a 3 by 3 identity matrix. So now I have 3 terms of V, each with, that's like these matrix multiplications times these scalars. So yeah, let me actually, I'm just going to rework the parentheses here a little bit. This is A times V. I can actually pull the V out here. Oops, I just make that little vector there. Let me pull the V out here. Sine theta A times V. So I'm just using the associative rule here. And so yeah, so at the end of the day, what I can do is write this as this matrix R. I'm going to say R is the identity matrix. So now I'm just going to factor out V. So R is the identity matrix plus 1 minus cosine of theta times A plus sine of theta times A. And that's it. So yeah, I mean, depends on how you want to do your parentheses here, but so this is the equation for the matrix R. If I multiply this by V, I'll get this, and I just showed that that's equivalent to another form of Rodrigues' rotation formula. Okay, so let me check it, see if I got it right. So I'm going to say here, R2 is equal to the identity matrix, which in NumPy is mp.I. So I'll have you do this as an exercise in GL matrix in JavaScript, but I'll just show you NumPy for now. So plus the scalar 1 minus cosine of theta. So scalar multiplied by this matrix multiplication here. That just means that I'm going to scale every element of the matrix by this. So 1 minus cosine of theta times A matrix multiplied by A. Turns out this is how you write that in NumPy. So that's matrix A times itself plus the sine of theta times the matrix. Okay, let's see. Moment of truth. Did we get it? Oh, whoops, I forgot to define A. So I actually need to... okay, so given the axis of rotation here, I need to create this matrix here. So okay, so it's 0, negative AZ, AY, AZ, 0, negative AX, negative AY, AX, 0. Okay, so that's R2, and that's starting to look pretty familiar. So basically, except for, oh, there is, okay, it's not quite there. Let's see. I got excited because I saw the first element looked right. But something is a little bit off here, so let me just check that real quick. I see what the problem is. Okay, so we actually ended up getting the inverse of the matrix we were looking for. In other words, we got a matrix that rotated the other way, clockwise by this angle instead of counterclockwise. If you look at this matrix, you notice that it's the same. It's just been reflected across the diagonal. So in fact, if I print r dot r2, you'll see this is basically the identity matrix. So It's basically 1, 0, 0, 0, 1, 0, 0, 0, 1. So I actually computed the inverse. And the reason is, so the arc cosine here, when I did this didn't actually tell me that if it was a negative angle or a positive angle. And so there's some ambiguity there. And so it just turns out that I really actually wanted this angle. I would have had to inspect that to get that right. So I want the negative of that angle, or 2 pi minus that. And now I actually get the right matrix. So let me just double check that. So that was R2, and this is R. So yeah, you got to check to make sure. Did I want the positive angle or the negative angle? Well, that's just when you're doing this conversion. Yeah, so that's actually more in this step when I'm converting from a rotation matrix to axis angle. But going from axis angle to this is rock solid. Like, you just follow this formula and you've got it. So I'm going to have you try that out now. All right, so anyway, I hope you enjoyed this. I really got into the nitty-gritty of Rodrigues' rotation formula. I hope this ends up being clearer than how it's presented other places, because I didn't focus so much on all the derivation. I tried to focus more on this intuition here, and we were still able to code it up even if it wasn't in its final form. Okay, good.